So, good afternoon. Thank you for coming here to this introduction to IoT reverse engineering with an example on a home router. I know that the time after lunch is the most sleepy time of the day, so I hope you will find this presentation interesting enough to keep you awake. My name is Valerio di Giampietro. I am an Italian. I am passionate about electronics and technology since when I was a child. For this reason, I studied electronic engineering at university and started working as a digital hardware designer, but soon I moved to a Unix system administration position and later to an IT infrastructure manager position, managing servers, but on the cloud and on-premise, managing storage, networking, databases, and so on. I am also a Linux enthusiast since 1993. My personal homepage is Valerio, written as va.ler.io. You will find a copy of this presentation and, more important, links to everything I will talk about today. My email address is Valerio, written as v@ler.io, and my Twitter handle is Valerio. Being a nerd, I am quite proud of these addresses. What we will talk about today, I will start with a short introduction about reverse engineering and then describe the reverse engineering process based on information gathering, building an emulation environment using KEM where to run interesting IoT binaries, then analyzing how the device works, and then at the end, modify the firmware that is our target. To define reverse engineering, we have to first define what engineering is. We can say that engineering is the science of making things that starts with the product requirements, continues designing the product, and finish building or manufacturing the product. The reverse engineering process is exactly the same process, but done in reverse order, and usually with a limited scope. So we start from the product manufactured by someone else, we analyze the product, we take measurements, and we reconstruct the design and the requirements. In our home router example, the limited scope is to understand how to modify the router firmware to add features and additional programs. We'll start with information gathering. The first information we need is who makes the device. In this example, it is the D-Link that makes the device. But we also want to know if there is an original design manufacturer, because sometimes a company makes the device, but another company has designed and developed the firmware of the device. We start opening the case, trying to identify the main device components, and we are especially interested, and it is very important, to the UART and the JTAG interfaces. At the end, we want to get the firmware and the root file system of the device. In this case, in this example, we open the case and start looking at the main board top. You can see that it's not easy to identify each electronic device because some devices are hidden below that black heatsink and also below that metal sheet used to shield radio frequencies. Anyway, we are able to identify some devices, and in this case, we are able to identify the UART that is clearly marked on the PCB. I wasn't able to confirm the position of the JTAG interface in this case. Looking at the bottom of the board, we can identify some additional devices, like, for example, the NAND flash device and the Wi-Fi module, but I wasn't able to identify the system on a chip. Maybe it is hidden below that metal sheet used to shield the radio frequencies. Locating the UART interface is very, very important. On the right, you can see the UART position on some miscellaneous boards. The first step, we start searching on internet to see if someone else has already done the job for us, identifying the UART interface on our device. Otherwise, we have to identify potential serial headers candidates. Sometimes these are marked on the PCB screen, so it's easy to identify. But otherwise, we have to identify 4 pins that are power, ground, TX, and RX. We can use a multimeter to find potential candidates. It is easy with the multimeter to identify power and ground. TX usually is a pull-up resistor, and RX usually is a high impedance input. We can also, if we know the system on a chip and if we have its datasheet, we can identify the UART interface on the chip itself and try to follow the PCB traces. This is not easy to do the multi-layer board. We can also use tools like Jtagulator. Jtagulator is a fantastic piece of tool. It has a lot of headers that we can attach to potential headers candidates, but for the UART and for JTAG interface, it can run some automatic scanning logic, and it is able to identify the pinout of the UART or of the JTAG interface. We can also use an oscilloscope or a logic analyzer to locate the TX pin, because for sure during a boot something will be written on the serial console and this pin will go up and down. But maybe this is a bit overkill. We also want to locate the JTAG interface. The JTAG interface is an industry standard for testing printed circuit boards after manufacture and allows access to many internal signals of complex integrated circuits. It also allows access to read-write flash memory content and can be used as a primary means for an in-circuit emulator. Multiple devices are daisy-chained together, and each one of them can be accessed using the JTAG interface. It has 4 or 5 signal pins that are test clock, test data in, test data out, test mode select, and test reset. Test reset is optional because we can reset the interface also using the other pins. To locate the position of the JTAG interface is not easy because there is no standard pinout, but anyway, there are few popular pinouts that are available on the URL shown on the slide. On the right side, you can see some examples of popular pinouts. So the first step is always to search on the internet to see if someone else has already identified the position of the JTAG interface in our device. Otherwise, we start looking for headers labeled TCK, TDI, TDO, and TMS. But if no label has been found, we have to look for potential pin headers candidates arranged in a row of 5 or 6 pins or in a double row of 10, 14, or 20 pins. We can use a multimeter to identify power and ground. This is easy. We know that TMS and TDI, usually, they have a pull-up resistor. The test reset can be pulled up or pulled down. TDO should be high impedance. So with the multimeter, we can try to identify some of this pin, then match what we found with popular pinouts, and this way try to identify the pinout of the JTAG interface. Otherwise, we can, if we know the system on a chip and this data sheet, as before, we can identify the position of the JTAG interface of the system on a chip and try to follow the PCB traces. Or we can use tools like Jtagulator, as seen before. After we have identified these interfaces, we have to repopulate them. This means to attach headers to these interfaces using a desoldering pump and a soldering iron, and then use a connector. In this case, it is a USB TTL serial adapter to connect the IoT device to the PC with a terminal emulator running PuTTY. But why we want to repopulate the interface and why we are so interested in these two interfaces? The UART is really, really important because it allows us to watch what is printed on the serial console during the boot, and this allows us to identify the bootloader and operating system version. Because I want to modify the firmware, we can also watch what it is printed on the serial console during the upgrade cycle and maybe get some information on how the upgrade is done. We have to use an USB TTL serial adapter and a terminal emulator on a PC, like, for example, PuTTY. We also are interested in the JTAG interface because it allows us to read the firmware from the flash EEPROM, allows us also to break into the boot cycle and use the JTAG interface as a means to do in-circuit debugging. To do so, we have to attach a board like Bus Pirate to the JTAG interface, and we have to use an open source software like OpenOCD to dump the flash EEPROM and to do in-circuit debugging. Anyway, to do this kind of things is really, really hard. The last step of information gathering is to get the firmware file. We always follow the easiest path first. This means that if the supplier has a website with the firmware updates, we go and download the firmware file from there. If the firmware update can be downloaded directly only by the device, we can sniff the communication with the Wireshark and get the firmware file. If the above steps are not available, we have to download the EEPROM image through the JTAG interface using Bus Pirate and OpenOCD. Once we have the firmware file, in this case I downloaded the firmware file from the supplier website, we want to have some information from this firmware file. On Linux we can use the file command, but this tells us that we have just a data file. But there is a very good piece of software that is Binwalk. Binwalk is able to scan inside a data file, searching a lot of different signatures of many file system images, of image pictures, of digital certificates, of compressed data, and so on. In this case, Binwalk tells us that we have a JFFS2 file system image and a gzipped compressed data segment. JFFS2 stands for Journaling Flash File System version 2 and is quite popular in embedded devices with NAND flash file system. We are also interested to extract the content from the file system image because we want to see the root file system. To extract the content, we need the Jefferson program to install on our Linux machine because the JFF2 file system runs on top of the MT driver that operates differently from the block device driver and cannot be loop mounted. But once we have installed Jefferson, we can use Binwalk to recursively extract the content of the firmware file. In this case, with the -E option, we can see that Binwalk extract the first file that it has extracted is the gzipped data segment that is a tar archive containing some packages, some board-specific packages. The second file, 200.jffs2, is the file system image, and the third folder, jffs2-root, is the file system image that has been recursively extracted into the file system. Looking at what was extracted, it seems that we have 3 file systems. In reality, we have only 2. This is a glitch of the Jefferson program. The first file system is the boot file system. We see that we have 2 files. One is cferam.00, that it is the bootloader image based on the Broadcom common firmware environment. The second file is the Linux kernel in an unusual CFE compressed format. If we start looking at other files and start doing some file system analysis, we can see that the system is based on BCBox. Using the strings command, we can also identify the BCBox version. BCBox is quite popular in embedded devices because in a single binary, it implements a lot of different functionalities like the init process, the bash interpreter, ls grep, and many other devices. Using the cross toolchain redelf command, we can also understand that the system is based on musilibc. Musilibc is also quite popular in embedded devices because it implements a lot of functionality of the libc library, almost everything the GNU libc implements, but with a much smaller footprint. We can also look at other libraries, for example, the libgcrypt library and other libraries and their version. So now that we have done some preliminary analysis, we can attach the serial console to the PC running PuTTY, and we power up the board and start looking at what is printed on the serial console during boot. We can confirm that the bootloader is a CFE. We can also identify its version. We can have the chip ID. In this case, it is a Broadcom chip. There are not so many information about this chip on the internet. Probably is a custom-made chip because Broadcom allows its customer to build chips putting together a processor core and some other devices. But anyway, we know that it has a processor core, that it is an ARM Cortex A9 dual-core CPU running at 1 GHz. We also can identify that it has 256 megabytes of RAM and 256 megabytes of flash EEPROM. We can also identify the Linux kernel version, that it is 3.4.11 with real-time patches 19. The instruction set is the ARM v7 instruction set, and the JFF2 file system, among other things, supports the non-standard feature that is the LZMA compression. We can also identify how the NAND flash is partitioned, and we can also confirm that BCBox is the init process, and that the first script started is the RCS script. This is according to the init tab configuration file. During boot, we can also identify the string epicentro software version. If we search on the internet for this string, we can identify the original design manufacturer. So this router was made by D-Link, but the firmware was developed by a Swiss company called ADB. So summarizing what we have found till now, we have found that our router is based on an ARM v7 Cortex-A9 multi-core processor that has 256 megabytes of NAND flash, that uses a Linux kernel that was released in 2012. This router started shipping in 2018, so it is a 6-year-old Linux kernel. We can also identify the version of other components, like MusiLibC was released in 2012, BCBox in 2010, libgcrypt was released in 2009, and we also identified that the original design manufacturer was ADB. As you can see, we have all the software or a new device. We can ask why it happens, probably because the maker tried to save some money reusing something that it already has, or maybe reusing some software development kit that was released by the chip manufacturer. Anyway, from a security point of view, this is quite bad because we have a new device with all the software, potentially with all the software with some unpatched vulnerabilities. Now that we have done, we have finished the information gathering process, we can start to build an emulation environment. We want to build an emulation environment where to run IoT binaries. We have to choose an emulation system to emulate, first of all, to emulate our processor, and we use QEMU. QEMU is a fantastic tool that emulates a lot of different type of CPU and a lot of different boards. In this case, we choose the VExpress A9 board with the Cortex A9 processor that is the same CPU as the one in our IoT device. But we not only need to emulate a processor, we also need a kernel and a root file system to emulate our environment. We could think of building everything by ourselves, cross-compiling everything, but this is an almost impossible task because of a lot of interdependencies among packages, libraries, device drivers, and so on. So we have to choose a build system. There are open source, very popular build systems. The most popular one is the Yocto project. It is very powerful. It not only builds a root file system and a kernel, but it is also able to build a custom Linux distribution with an included package manager. But its main drawback is that it has a steep learning curve. Another popular build system is buildroot. It builds only the root file system and the kernel, but it is easy and fast to learn and has a very good user manual. Another popular build system is OpenWRT, later renamed LIDE. It is tailored to build a replacement router firmware, but the documentation is scattered in the website and it requires more time to learn compared to buildroot. For this reason, in my home project, I choose the buildroot. Choosing buildroot is not enough. We want to have a root file system that is compatible with what we have on IoT device because we want to run IoT device binaries. So we are also able to choose a buildroot version because we want to have a root file system that is based on same components that we have on the IoT device. So it has to be based on the same MusiLibC version. It must have a compatible libgcrypt crypto library. It must have the same kernel. And also other libraries should have compatible version on what we have on our IoT device. So the buildroot version to use is buildroot that was released on February 2014. Unfortunately, due to the dependency hell, this version doesn't run on a recent Linux distribution. So it doesn't run on Ubuntu 16.04 or Ubuntu 18.04. So we have to use an older Linux distribution that is more or less the same age as the other components that was released, so we can use Debian Wheezy, that was released in 2013, and we will run this in a Docker container using Docker as a light virtualization environment. So we have to build the Docker file for Docker container. This is a minimal Debian Wheezy container with just the packages needed to run build root. Docker file is available on my GitHub repository. The important thing when we run Docker is three important choices. We map the temporary X11 folder of the host machine inside the same position in the Docker machine. This is to be able to run graphical programs in the Docker machine, as for example, the make xconfig command. We also map the home directory in the host machine inside the same position in the Docker machine, and we map username and userid in the host machine to the same username and userid in the Docker machine. In this way, we can have a system with, for example, two windows. One, it is the host window running Ubuntu 18.04, and the other one is the Docker machine running Debian Wheezy, but the two windows share exactly the same home directory and exactly the same username and userid using the sharing of information and files. Build root must also be configured because we want to build this root file system as we want. So the configuration starts with a shipped configuration file shipped with the build root that is based on our emulated board, that is the vExpress board, but we have to do some modification. The most important modification is that we want to build packages and libraries with the debugging symbols and other debugging information, because we want to be able to run IoT binaries in our environment. They want to be able to use the GNU debugger, and at least we can put breakpoints on library functions entry, and we can understand what the binaries do, looking at what library function calls and what are the parameters used in these function calls. We also want to build debugging tools like GDB, GDB server, and so on. And we have to include the driver for the NAND flash and the JFF2 file system. We also have to include other libraries used in the IoT device. We also have to do some minor kernel configuration. Basically, we select the same board with device tree support. We select the preemptible kernel as in our IoT device. We have to include the NAND device support and support for NAND flash simulator. And obviously, we have to include the support for the JF2 file system with LZMA compression. We also have to do some minor configuration for the muslibc. This is the result of trial and error. For example, we have to include native POSIX threading and so on. And we also have to include some debugging symbols also in the muslibc configuration. Due to some quirks in this configuration, we have to do it in some more complicated way. I go fast because I have to be shorter than originally anticipated. Sorry. Because we want to replace the firmware, the original idea is to modify the firmware file to load the firmware using the normal upgrade process. So we want to analyze the upgrade process on the IoT device. We start the upgrade process using the web interface and start looking at what is printed on the serial console during the upgrade. In this case, we can see that is printed on serial console that the script that starts is upgrade prepare.sh, but then the script upgrade.sh is started. It prints signature OK, so this means that the firmware file is assigned. Then a flash erase all command is executed to erase the third partition. This is the partition dedicated to the firmware upgrade. And then the dd command is used to extract the root and boot file system from the firmware file, and the NAND write command is used to write this boot and root file system to the NAND flash device. After this, some kernel module does a partition split on the fly and create two new partitions that are boot fs2 and root fs2. Looking at parameters in the dd command, we can identify where in the firmware file the boot and root file system are located. We can see that some packages are added in the new root file system. These packages were included in the gzipped compressed data inside the firmware file. And then the bootloader is written again in the flash EPROM, and then the router is rebooted. So, summarizing very shortly, the most important script to analyze, to be able to understand how the upgrade firmware works and how we can modify the firmware is upgrade.sh. The firmware file is signed and the signature is checked with the sig_verify binary that is included in the root file system of the router. The boot and root file system are written in a single and the write operation. Some kernel module is used to split the partition on the fly. Some other kernel module is used to delimit the end of the root file system partition. Some additional packages are added at the end based on board type, and the bootloader at the end is written on the NAND flash and the system is rebooted. So if we want to modify the firmware, we have seen that the firmware file has a signature. So we want to understand if we can fake the signature to be able to load our own firmware file. Because the signature is checked with the sig_verify binary, we want to execute this command in our emulated environment to understand what it does and to understand if we can fake the signature. Sig_verify, as all other binaries in the router, is a stripped binary. It has no debugging information, but it calls library functions. So the idea is to run this executable in our emulation environment and putting a breakpoint on each library function entry. We can have a list of all library functions called by the sig_verify binary with the cross-toolchain readelf command with the shown parameters. In this case, we have a list of all the library function calls. We can run sig_verify GNU debugger using the GDB server in the emulated environment and the cross-toolchain GDB in the host system. These two will talk together, and on the host system, the GDB will do the hard work of showing a breakpoint, variable contents, source code, and so on. Doing this kind of analysis, it is possible to clearly understand what sig_verify does. Just looking at the library function calls that it does. Basically, it reads the last 256 bytes from the firmware file. This is the signature. Then it calculates the SHA-1 checksum of the firmware file using the libgcrypt library functions. Then it calls other libgcrypt library functions to to verify the signature, passing as parameter the SHA-1 message digest calculated, passing the signature and the public key. The signature is the original SHA-1 message digest encrypted with the private key, and the public key is used to decrypt the signature and to see if it matches with the calculated SHA-1 message digest. If it does, it returns OK. Otherwise, it returns an error. The public key is based on two big integers or multi-precision integers that are called the modules and exponent. Using the GNU debugger, we can dump these two big integers from memory, and we reconstruct the public key in the standard .pem format. But unfortunately, the private key remains unknown, so it's not possible, and it's not included in router's certificate files as expected. So this means basically that it's not possible to modify the firmware using the standard firmware upgrade process because we don't know the private key and we cannot fake the signature. So we have to find another way. So we start finding another way. We can see that in this case, the router allows a telnet SSH connection, but present a Cisco-like restricted shell. Cisco-like means that if we type help, we have a list of all available commands. The commands are also auto-completed, and if you type a question mark, all the options are shown, but that's all. Doing some file system analysis, we can understand that this restricted shell is based on an open source project that is called Clish. Analyzing the startup script, we can understand that the configuration files are located inside /tmp/clish directory, and this is a link that points to a folder in normal mode and to another folder in factory mode. So we can start analyzing the startup script, for example, in normal mode, to see if we can find something interesting inside. In this case, we find an interesting command inside that is factory mode. This is an hidden command. Hidden means that if you type help, it's not shown, and it is not also auto-completed pressing tab. Because of this means that it is an interesting command. So we execute this command, and the routers enters the factory mode and reboots. Factory mode is a special mode. We have no normal Wi-Fi, no internet connection, no DHCP server, and so on. But it has an interesting command. It has a non-privileged shell login. So it has the system shell command that gives us a normal Linux shell. This is a normal user Linux shell. So we cannot modify the system, but we can explore the system. So our target is to become a root. So we start looking for processes running with the root privileges, trying to find something to hack to become root. So we start identifying each process and executables. We can use the strings command to see the strings inside. In this case, identify what this process does and its version. We can also try to run these executables in the target itself or in the emulated environment with the -v for version or -h for help command to identify the program in this version. In this case, in this way, we can identify all open source executables and their version, and we can search the internet for known vulnerabilities for the specific executable version. If some vulnerability is found, we have to check that this vulnerability is exploitable in the specific IoT device configuration, because often we have vulnerabilities that are exploitable only under certain circumstances. If no exploitable vulnerability has been found, as in this case, we have to select a process candidate to reverse engineer in our emulated environment to find vulnerabilities. Operating system binaries with no known vulnerabilities are hard to crack, because if nobody else have already found a vulnerability, it will be difficult for us to find one. Lower level stuff, like stuff related to DNS or VoIP or other special devices, usually are more difficult to crack because they do one specific thing and they have a smaller attack surface. Higher level executables, like with the bigger configuration files, usually are less difficult to crack because they have a larger attack surface. Analyzing the process, the most interesting one is the configuration management process. It runs as a root in background, and it does all the root configuration changes, like adding new users, configuring the DHCP server, changing router address, and so on. Analyzing startup scripts and executing CM in the emulation environment, we can discover that this process uses shell scripts to carry out its duties. On the router, there is also the CM client command that is executed by, as a normal user, by the web interface and by the restricted shell that talks to the background CM process to do the change. In this way, it seems the router seems well designed, because in this way, only permitted configuration changes are allowed. But doing file system analysis, we can see that CM client is used in startup scripts to configure the CM process. So in a startup script, there is, for example, that command that tells to the CM process to load all the XML configuration files available in that folder. One of these configuration files is management.xml, but others are similar. That is inside this interesting snippet, when basically it tells to the CM process to use the users.sh script to change users' properties or to add new user. So the idea is we can copy the management.xml in our own folder, modify it, reconfigure the CM process using the CM client that runs as a normal user. We can modify inside the fake management.xml just to execute not the standard user.sh, but our own version that we call fake users.sh that does same thing as the original, but just with a few instructions to modify the password file to remove the root password. we can then trigger the execution of fake_users.sh. It will be executed by the same process as a root, and will be able to modify the password file. We can put together all these steps in a script, and then we can copy this script as a normal user on the device. We can make in the device this script executable. We can run this script, and having removed the password for the root user, we can do NSU and become root. So now we can find everything we want. But our target is to modify the firmware. So basically, based on firmware analysis of the firmware upgrade script, we can understand that the firmware file is the following structure. We have an MD5 checksum, we have the boot file system, a partition splitter, the root file system, and then the partition marker, at the end the signature. So our idea is to modify just only the root file system. So we can extract the root file system from the firmware file, modify it, create the new root file system image modified, pad the file system image to the same size as the original root file system image, because in the firmware files there are many fields that we don't know their purpose and we don't know how they are recalculated, changing the root file system size. If we need additional software to be installed on the router, we can use an USB key that has additional storage. At the end, we can reassemble everything, putting everything together using the dd command, and in this way we have an unsigned firmware file. The problem is that we cannot load this unsigned firmware file with the standard upgrade procedure. But we are root, so we have some, we can do something. In the original upgrade script, the firmware is checked with these 2 lines of code. So the sig verify does the check, and the ret code variables returns the output of the return value of the sig verify command. So we can copy this script in a temporary folder, modify it to always return 0. This means always returns OK also if the signature check fails. And then we can temporarily replace the original script with our own version using the mount with the ---- bind option. The bind option in the mount command is usually used to mount a folder over another, but can also be used to mount a file over another. And an interesting thing is that it can also be used to mount a file over another in a read-only file system. In this case, we can temporarily replace the upgrade.sh script. Doing so, we can do now the upgrade with our unsigned firmware file, and the upgrade will succeed. So we have reached our target, that was to modify the firmware. So, conclusion, summary, we can say that reverse engineering can be really, really challenging. It is important to clearly define the limited scope of the reverse engineering project to remain focused on the target. It is important to start gathering information, always following the easiest path first. So if something is available on the internet, we can search this. Otherwise, if some information is missing or difficult to get, we try to move forward, and we go back only if absolutely needed. We can search on internet for everything, including known vulnerabilities. This is always the easiest path to do. And if we have to hack some process, we have to select process running as a root and with a large attack surface. At the end of this presentation, I have included a lot of useful links to some GitHub, my own GitHub repository, one with all the tools and a firmware modification kit for this router, another one to build the emulation environment, and other link to everything I talked about today. So unfortunately, I have no time for questions because time is quite short. And so thank you very much for your time and your patience.